Have you ever stopped to think about Earth's temperature? I don't mean over the last 100 years, I mean over its entire 4.5 billion year lifetime. Well, that's what we're going to do today. We're going to look at our planet's entire history through one single powerful lens: heat.
I mean, think about that for a second. Our planet has basically had a fever for its entire existence. It sounds wild, but it's absolutely true. From the second it came into being, Earth was this incredibly hot place, and its whole story, really, has just been one long, slow process of trying to cool down. So you gotta ask, where did this crazy planet-sized fever even come from? Well, it all goes back to its birth, which was anything but gentle. First, you add what's called violent accretion. That's just a fancy way of saying countless smaller bodies smashed into each other over and over, generating an insane amount of heat. Then, the big one, a massive impact with a planet about the size of Mars. I mean, this collision was so huge it literally created our moon and probably melted or even vaporized a huge chunk of the early Earth. And if that wasn't enough, as all the heavy stuff like iron sank to the center to form the core, that process itself released a ton of energy, superheating the whole interior. So this incredibly hot start basically set up the central drama of our planet's life. It's a story that's been playing out for billions of years. A constant tug-of-war between the heat being cooked up inside and the heat trying to escape out into space. And you can really break this epic struggle down into two main players. On one side, you've got the planet's engine. This is radioactive decay. Think of it like this. There are unstable elements, like uranium and thorium, buried deep inside the Earth, and they're constantly breaking down. This process releases energy, and that keeps the inside of our planet hot. Then, on the other side, you have the planet's radiator. This is mantle convection, and it's the main way all that heat from the engine gets carried up to the surface so it can finally escape. Okay, let's pause for a second on this idea of mantle convection, because it's super important. We're talking about the slow-motion churning of solid rock. Yeah, solid rock, over millions and millions of years. It's like a giant conveyor belt. Hot rock rises, it cools off near the surface, and then it sinks back down, bringing that heat with it on its way up. It's literally the planet's exhaust pipe. All right, so you've got this powerful engine constantly making heat, and this exhaust system trying to get rid of it. But what keeps things from going haywire? Why didn't the Earth just melt into a puddle or freeze completely solid billions of years ago? Well, it turns out our planet has a pretty clever trick up its sleeve. It's got a built-in thermostat. And this quote nails it. It all comes down to something called viscosity. Now, viscosity is just a word for how thick or runny something is, how easily it flows. And the amazing thing about the Earth's mantle is that its viscosity is totally dependent on its temperature. That simple relationship, that's the secret sauce for our planet's stability. So let's see how this thermostat actually works. It's a really elegant feedback loop. Let's start with the first scenario. What happens if the mantle gets too hot?
Well, when the rock in the mantle is super hot, its viscosity plummets. It gets way less sticky, way more fluid. The best way to picture it is like warm honey. It just flows really, really easily.
And since the mantle is flowing so easily, the conveyor belt we talked about, the convection, goes into overdrive. It speeds way up and becomes super efficient at dumping heat at the surface. The result? The planet cools down, and fast. The fever starts to break. Okay, so that's what happens when it's too hot. But what about the flip side? What happens if the mantle gets too cold? You guessed it. As the rock cools down, it gets stiffer and thicker. Its viscosity goes way up. Now, instead of warm honey, think about trying to pour cold molasses. It's sluggish, it barely moves. And that sluggishness slams the brakes on convection. That conveyor belt slows right down to a crawl. It becomes terrible at releasing heat. So all the warmth being generated by that radioactive engine gets trapped inside. This prevents a planetary deep freeze and allows the interior to warm back up a bit. It's a brilliant, perfectly self-regulating system. So, what's the big picture here? What's the result of this amazing planetary thermostat in action for billions of years? Well, you get something we can call the Great Cool Down. And you can see it right here in the numbers. Look at that massive temperature drop early on. That's the initial fever breaking as that super fast convection did its job. But after that initial plunge, the cool down gets much, much slower and more steady. That's the thermostat kicking in, keeping everything in a pretty delicate balance for the next few billion years.
So what about right now? If you measure the heat escaping Earth today, where is it all coming from? Well, about 75% of it is from that radioactive engine that's still humming along. But here's the kicker. A full 25%, 1 whole quarter of the heat is still just the leftover heat from when the planet was born. It's called secular cooling, and it means Earth is still, even now, shaking off the last bits of its original fever.
And you know what's really cool? For decades, scientists actually thought this was impossible. They figured convection was so good at its job that all that original heat should have vanished billions of years ago. The fact that a quarter of our planet's heat budget is still just leftover warmth, that's actually a pretty recent discovery, thanks to better models.
Okay, but this isn't just some abstract science lesson. This whole 4.5 billion year cooldown story has had real, tangible effects on our world. In fact, you could say it's given us a bunch of incredible gifts.
So let's ask the big question. Why does any of this matter to you and me? Why should we care about some ancient planetary fever? Well, because without it, the world we live in would be completely, and I mean completely different. Here's the first big gift. As the planet cooled over billions of years, the very center, the core, finally got cool enough for the iron there to start solidifying. And about 2.5 billion years ago, something incredible started to happen. A solid inner core began to form and grow right in the middle of the liquid outer core.
Now, this isn't like an ice cube freezing. This process of the inner core growing releases a massive amount of energy. Some of it is just heat, but the really important part is the gravitational energy that's released as the heavy stuff solidifies and the lighter stuff is left to slosh around in the liquid outer core.
And that energy, that's the fuel. That's what churns the liquid iron of the outer core into a frenzy, creating a powerful dynamo. And what does that dynamo do? It generates our planet's magnetic field. That invisible shield is the only thing protecting our atmosphere and us from being blasted away by the solar wind.
So let's just recap the gifts of this great cooldown. It gave us a solid inner core. That inner core powers our protective magnetic field. And don't forget the very engine of this cooling process, mantle convection, is also what drives plate tectonics, giving us our dynamic planet with moving continents, mountains, and oceans. Everything that makes our world geologically alive is a direct result of this cooling history.
So you see, from its fiery, feverish beginning to this long, slow, life-giving cooldown, the Earth's thermal story is really our story. The planet is still cooling, of course, incredibly slowly. And it just makes you think, as this ancient 4.5 billion year process continues on without us, what kind of planet are we building on top of it?